now that we know the definition of independent, it's time for us to use it to find a probability. This is the multiplication rule for n independent events. Now this is key. They're independent. It has to be independent for this rule to work. If they were not independent, we would be in a different section, which is more difficult, section 5.4. All right, what this rule says is that if you want to find the probability of event 1 and event 2 and event 3 and so on in sequence, so those events happen in order, then what you do is you multiply the probability of event 1 times the probability of event 2 times and so on. Hence, it's called the multiplication rule. Right? One other comment I can make in our course in general, if you're talking about more than one thing happening, it will be the multiplication rule that you're using. So we can just make a note. I don't want to actually tie it to the independence piece because it's not. It's actually just tied to the multiplication rule. We use this rule all the time. Whenever more than one thing is happening or occurring. That's key, right? So if you have 3 cards or 3 rolls of the dice or 5 people being drawn from this group, more than one person, it will be in the multiplication rule. The multiplication rule will somehow be involved. All right, let's put this into action. Suppose we have a standard deck of cards. Now notice what I wrote for every one of these problems. I put a little with replacement. I'm doing that because otherwise you are not in this section. You are in section 5.4. So all of them have with replacement because all of them have independence. So you can make a little note there. With replacement will mean it's independent. Which we need in order to be able to use this rule. And again, that's the only rule we are going to learn for multiple events. Well, other than the last rule, which we'll talk about later. All right, so we want to draw 2 cards at random with replacement. What is the probability that the first one is an ace and the second one is a heart? So see the and in there? Okay, so I want the probability of an ace first and a heart second. They're in sequence. See what I mean? In sequence, first, second, third, etc. Something's going to happen first, then something's going to happen, then something else will happen. So according to the multiplication rule, I just say the probability of an ace times the probability of a heart. Well, ace is 4 out of 52. Hearts, there's 13 out of 52. And then I can multiply. There's several ways to do this. We could reduce those fractions and do it that way. I can actually use the calculator, which is what I'm about to do. 4 divided by 52 times 13 divided by 52. This will give me a decimal answer, which is lovely and wonderful. If I want a fraction, I can hit math and hit number 1, enter, and it makes it a fraction. If you want to use Desmos, just a little reminder on how to use Desmos to find fractions. So 4 divided by 52, I have to kind of arrow over to get myself out of that denominator, times 13 divided by 52. You can see it's giving the decimal, and if I click over here on the left, it turns it into a fraction. So it's 1 out of 52, or 0.019, roughly. Either one of those is acceptable, depending on what you were being asked to do. All right, let's do it again. So you draw 2 cards at random. What is the probability that both of them are queens? Okay, so that means that my first card needs to be a queen, and my second card needs to be a queen in order for both of them to be queens. So that would be the probability of a queen times the probability of a queen, which is 4 out of 52 times 4 out of 52. You know, just for fun, I want to find out what 52 squared is. 52 squared would be 2,704. So this is 16 over 2,704. In case you're interested, the one above, was 52 out of 2,704. That's why, of course it was. That's why it disappeared. So let me pause and fix that real quick. So if you want to write it as an unreduced fraction, that would also be true. 52 over 2,704. This would be 16 over 2,704, which, let me see here. 16 divided by 2,704. And then if I hit this, it's 1 over 169, which was 0.0059. I guess I'll go 4 decimal places on these. So any of those is technically correct. Same is true up here. The 52 over 2,704 is just not reduced, but it's correct. All right, now what about the next one? Well, I'm increasing the number of cards. So for these first ones, there were only 2 cards involved. But for this one, there's 3 cards involved. All right, I want none of them to be face cards. Oh, this is going to be tricky. All right, so let's remind ourselves. Just do a little moment of recall here. The probability of a face card is 12 out of 52 because there are 12 face cards, 3 for each suit, and there's 4 suits. So king, queen, jack of spades, king, queen, jack of diamonds, king, queen, jack of hearts, and king, queen, jack of clubs. Say that fast. All right, I want them to not be face cards. So what's the probability of not getting a face card? That would be 1 minus 12 out of 52. In other words, there's 40 out of 52 non-face cards, right? Okay, now how has that helped me? Well, think about what you want. You want the first one to not be a face, and the second one to not be a face. I'm just going to put F there. And the third one to not be a face. So you want the probability of not face times the probability of not face 3 times. And if you're thinking, well, I could square or cube that, yes, you could. You could actually write it that way up here as well, because 4 out of 52 times 4 out of 52 is 4 out of 52 squared, right? So here I would take the not face, which is 40 out of 52. There's 40 out of 52, and I'd multiply it by itself. In other words, you're taking the probability of not face to the 3rd power. Like that. And we are going to make a computer do that. All right. So it's quicker and easier if I just use the fraction. So, or if I use parentheses. 40 divided by 52, close parentheses. And then to cube it, you raise it to using the caret button, to the 3rd power. And you get 0.4552. Like that. All right, what if I draw 5 cards at random? What is the probability that all of them are hearts? Oh, that's an easier question, actually. C is the hardest one because C has the negative in it, right? The negative voice means you're going to have to do the complement. But 5 is just saying all of them are hearts. So I want the probability of a heart and a heart and a heart and a heart, right? There's 5 of them. Okay, so that would be the probability of heart times the probability of heart 5 times. If you're thinking, this is tedious to write out, yes, it is. So what you could do instead is say, hey, take the probability of a heart and raise it to the 5th power. And this is a bracket, by the way. It's just a glorified parentheses. So if you want to use parentheses there, that's fine also. Well, a heart is 1/4 of the deck, right? It's 13 out of 52. You want to take 13 out of 52 and raise it to the 5th. In other words, you want to take 1/4 and raise it to the 5th power. I'll grab Desmos this time, just for some variety. All right, so if I grab Desmos and I say I want to take parentheses 1 divided by 4, then I close my parentheses and raise it to the, so using the caret button on my computer, 5th power. It tells me it's 0.000976. Okay? If you want a fraction, it will give it to you, right? So this is 1 over 1024, which is, I'm going to write this down, 0.000976. I don't even feel like rounding any less than that. However, if you did want to round to 4 decimal places, it would actually round, the 7 would round the 9 up, and it would become 0.0010, like that. Right? It rounds the 9 to a 10, if you will. All right, did you catch something? I don't know if you did. Let's see if we caught it. Did you catch the words? Both, none, all. They all meant and, right? They mean this and this and this, right? But we didn't say and, but that's what we meant, right? Which is my comment right down here, which is that the wording on these problems is very important. And in English, and hides a lot. And is in words like, well, both, all, and none are the most common ones. But even if I said 7 of them are this, this happens 3 times, you'd multiply, right? They all imply multiplication. Now, one other thing to keep in mind is that this is keeping us out of having to do tree diagrams and all of that jazz, right? This works really well for large sample spaces. I mean, this is a very large sample space, and it was no problem for us, right? We were able to just put it right into a formula. So it means we can avoid a tree diagram, which a tree diagram would be a nightmare. We don't have to deal with it. It all is taken care of for us by the multiplication rule. So it's a very powerful rule. We really like it. And you will always use it when you're doing multiple things. I can't stress it enough, right? So we use this rule when we're doing more than one thing. Whenever you're doing more than one thing, you're essentially using the multiplication rule in one form or another.